everyone. Our senior design project is focused on macroalgae, specifically biofuels off the coast of California. My name is Eric.
My name is Nils.
I'm Catherine.
I'm Ben.
And our project is based off an initiative by the Department of Energy calling for the use of renewables. And in our case, we're looking at macroalgae, specifically Macrocystis peripherea, otherwise known as giant kelp.
So our project was broken down into milestones. The first one was to determine which factor would influence kelp growth and which one were the most important. For example, the temperature of the water or the depth of the seafloor or the hard constraints, shipping lines, etc. And for each factor, we are going to build an index function which will range from 0 to 1, 0 being impossible for kelp growth and 1 being optimal.
The main part of this project is to visualize these factors. So we're creating a map to help farmers visualize the best locations for kelp farming.
So basically we're creating MATLAB functions that will change whatever data, for example, NOAA temperature data, into basically our index notation, which will then be weighted and added into the total index. And eventually we'll create an overall index including all our factors that will range from 0 to 1, and we will plot that on a map of the Southern California coastline, where areas that are good for kelp growth will be denoted in red and bad areas will be blue. And whoever is interested in farming kelp will be able to type in the location, and our function will return if that's a good area or not.
Now here's an update of our progress thus far this quarter. The first thing we did was some background research so as to better understand kelp and how it grows. We took a look at current kelp farms, specifically in Chile, to get an idea of the scale of farms that could be used. The same giant kelp that grows off the coast of California also grows off the coast of Chile, so it was a good comparison. Then we analyzed kelp biology to understand its nutrients requirements, which play a key role in its growth, and therefore dictate where farms can be placed. Using the farm comparison and kelp biology information, we were able to put together a factor list to guide the placement of kelp farms. Hard constraints, like marine protected areas, operational factors, like distance from port, and growth factors, like temperature, are all being factored into our index equation.
For our experimental methods, we are using mainly MATLAB to create functions for our indices and maps that display those indices. AquaMapper didn't provide sufficient data, but we did pull data for sediment types.
The objectives of our project are to generate a map for optimal kelp farming using a MATLAB script. And this script takes inputs of latitude and longitude, and it will output the total and individual index values for all of our factors. And we've created an individual function in MATLAB for each of our factors, and we've been taking data that's been given to us by our sponsors and adjusting the data using our functions to create an array of 0 to 1s, which are then plotted on our map. And all of these functions have adjustable boundary conditions, such as maximum and minimum temperature, that a farmer or an interested party would be able to change. And at the very end, we will determine weighting factors that will be used to create our final index for our final map.
Here's an example of a code for the depth index function. As you can see, everything is in terms of variables and not actual values. That way, a farmer can set their own limits for depth in the lines 17 to 20 of the code and have an index function that would work the same way. In this slide, we can see a graph for the depth index function where a linear relationship was assumed between depth and the index values outside of optimal depths. The second graph is another example of an index function for total nitrogen. Here, a Michaelis-Menten relationship was assumed as this factor represents a chemical reaction, and the only variable the farmer would have to change would be the KNO value, which is the value at which the index would be 0.5.
So for coding our maps in MATLAB, we've been receiving data in the form of NC files and shape files, and then we read these into MATLAB as shown in lines 1 through 6. And we adjust for some of the data to make the processing quicker by getting rid of array values that we don't need, which is shown in lines 10 to 16. And we use mmap to create a projection of our desired latitude-longitude values, and then contour plot with our given data.
For our milestones, we completed our first milestone, which was to determine the suitability index and the factors included. Our second milestone, which is the bulk of our project, is to create the suitability index maps. Right now, we are putting all the data, such as nutrients and temperature, on a single grid. We still need to combine those indices with weighting onto the map. Right now, we are also touching upon our third milestone by outlining the output given our coordinate inputs.
Here is our current map with depth, bathymetry, and hard constraints information. As you can see, the appropriate depth for kelp farms leaves only a small sliver of ocean area along the coast that is optimal. With this in mind, and the large areas covered by marine protected areas, most farms will have to be right along the coastline. Ideally, some can also be placed around Catalina Island since it offers additional low-depth area. Catalina Sea Ranch is the proposed test site for the first kelp farm, and once it is up and running, then we can compare its success to the rest of the optimal locations.
The rest of the project will consist in mapping the rest of the factors, determining the weighting factors for each of them, and come up with a plan for uncertainty. An example of uncertainty source is linked to sediment type. As you can see on the map in this slide, the data is only given for small regions, and there are large areas with no data available. To deal with this issue, we would need to decide how we will determine which type of sediment are in those empty regions, meaning what kind of interpolation to make, possibly linear interpolation, or simply choose the closest sediment type, for example. Hopefully, uncertainty will be included in our final index so farmers could take it into account.
Our primary end result will be a color-coded map based on the finalized index, which is normalized by the sum of all the individual weighting factors. Additionally, we plan to have unique index maps for each factor before they are weighted and implemented into the final model. This way, a farmer could see which factors are the limiting factors in a certain area. Our MATLAB script will also print the index values for each data array value if desired.